Hi everybody, this video is about double integrals. So we've been doing some differential calculus with multiple independent variables. So we know when we had just one independent variable, we had the derivative, it gives us the rate of change. How does y change as we change x? When we add a dimension to that, we've seen that with a function of two independent variables, so we're no longer talking about a curve in space, but perhaps a surface, and we had, instead of just the derivative, we had two different partial derivatives, one for sort of each coordinate direction you could head in. And we could use that to look at derivatives in any direction, but these two form a basis for that. And so instead of just one derivative, we've got two partial derivatives. And now we can look at what's going on with integral calculus. What happens when we look at integrals with multiple independent variables? So with a single independent variable, our function just gives us a curve in the plane. And the definite integral gives us the area underneath that curve. And so the way you saw this when you were in single variable calculus was you looked at the Riemann sum that comes from looking at the area of a bunch of little rectangles, and then you took the limit as the number of rectangles goes off to infinity, and their width shrinks down to 0. You look at that limit, and we get the exact area under the curve instead of an estimation. I'll draw the estimations so that we have that sense of what's going on. But this picture informs what's going on in the limiting case. So how does the definite integral get us the area underneath? Well, the function gives us the height of every rectangle. So at any given x value, we could use that to find the height of a rectangle. And then we look at the width of those rectangles being some tiny sliver of the x-axis. And then the product of those two things then being the area of a rectangle. And then so we just added up every rectangle over the portion of the x-axis that we cared about to get the actual area under the curve. And so that's what the definite integral was with a function of a single independent variable. Well, now that we're looking at functions with multiple independent variables, we're instead, as I mentioned, looking at a surface. And so instead of finding the area under a curve, we're going to find the volume under a surface. But it's going to work really analogously. It's the same setup. We're going to, instead of looking at rectangles, we'll look at right rectangular prisms, for instance, is one way to do this. And so if I look at a bunch of right rectangular prisms from the xy plane up to my surface, whatever height z that it's at, we can use double integrals to find this volume. And so the value of the function gives me the height of one of these rectangular prisms. And we can use some sliver of the x-axis to get, say, their length. And we can look at some sliver of the y-axis to give me their width. And so the volume of one of those rectangular prisms is the product of those three things. And so we just need to add up the area of a bunch of all the different rectangular prisms. And of course we'll shrink this down to infinitesimal changes in x and y to get this exact. But the notation we'll use is two integral signs, so double integral. And I put the a just because we're talking about integrating over some area in the xy plane. And we'll spend more time talking about this in class, but we'll look now at a fairly straightforward example to sort of see the mechanics of how to compute these things. But that's what the double integral is going to find. Over some area in the xy plane, it gives me the volume of the volume that's underneath the surface described by my function. Okay, so on to our example. For most of the functions that you're going to come across, well, we'll be talking about anyway, if those nice functions we can compute double integrals by doing what are known as iterated integrals, which just means we can do an integral with respect to one variable, and then an integral with respect to the other. And so much the same way that we've done partial derivatives, let's say we do, this inner integral first. So we integrate our function with respect to y across the particular bounds given for y, in this case from 0 to 2. And that in that case, we're treating x like a constant, just like we would if we were taking a partial derivative with respect to y. We treat the other variable like a constant. When you integrate this and evaluate from 0 to 2, the y's are going to go away. They'll drop out, and you'll just have some function of x, which you can then integrate with respect to x. So then you perform the outer integral. So it's sort of like the layers of an onion. So for nice functions, you can do this. We can just integrate with respect to we can do sort of the inside integral and then do the outside integral with respect to the appropriate variables each time, being careful about the bounds. So the 0 to 2 goes with y in this case, and the 1 to 3 goes with x. So take a moment to compute this integral, see what you come up with. If I didn't make any mistakes, I believe you come up with 88 over 3. And then I've got a question, which is, what happens if I integrate the exact same function, but in the opposite order? So instead of integrating with respect to y first and then with respect to x, I'll integrate with respect to x first and then with respect to y. And note that I also swapped the bounds on those integrals, so the upper and lower bounds, so that we're still talking about the same area over the plane. So what do you think's going to happen here? And then take a moment to compute it, and we'll talk about this in class.